Hi everybody, we are back. Quadrante is back to All Plan Day in 2023. Last year was a real challenge for us, but this year it's the bigger challenge for us and for our teams and collaborators. Our BIM technology and know-how continues to improve based on All Plan. Last year we showed here on this day the Ruby line, Metro do Porto Ruby line. We were doing the viaducts, the stations, retaining walls. We have done all that, we have delivered, we have coordinated the BIM models, and at the end we really ended doing much more than we thought at the beginning. But that has improved the quality of the project, and at the end it has been a pleasure to work in this way. Now in 2023 our challenge is different, and now we continue to work in the railway sector, but now in a heavy railway. Okay, here you can see the Cano Maradi-Dutse railway line. It's a standard gauge railway line. It's located in the north of Nigeria. It's a big country railway line that we are designing. This area of the country is less populated, yet has security issues, and so the number of men in the field and the necessity to implement workflows to allow for the quick construction of every bridge and also, of course, of the railway line and stations and yards needs to be carefully planned in order to implement maximized construction efficiency with a minimal schedule. The railway line, we say, that starts at Cano. Okay, it has the main branch until Maradi, crossing the border for the Niger, and it has a secondary line, let's say a second branch to Dutse. So this is the Z-shaped configuration. We are doing all the detailed design, but only components of this design are in BIM. Bridges, overpasses, underpasses. So this is one of the railway bridges that we have designed. This is a simple design, an efficient construction design. Our concern is the economy and the duration of the construction without forgetting the aspects of the maintenance and the reduction of costs during the operation of the railway line. In terms of the bridge, we are talking about a girder deck with prefabricated beams with pressed truss tendons. The spans are simply supported. The slab deck concreted over a prefabricated slab. So at the end, the functioning of the deck also comprises the slab that is explained along 4 or 5 pages manual that allows for the transformation of our template to the final bridge. So let's go to the bridge and try to look at with more detail of how we produce this. So when I open All Plan Bridge, what I see is this. This is a finished bridge. Here you can see some elements that were not present on the final in the All Plan engineering, and these are these vertical laminar elements. These vertical elements are in fact used to produce Boolean operations to construct the joints between the prefabricated slab elements and the elements for the leads on the sidewalks, and so that's the reason. Also, we have secondary elements that I will explain in a little bit, but I just wanted to start and to clarify why the difference of image between this model and the previous one that I showed in the All Plan engineering. The railway axis was imported from BIM Plus using the length XML, of course, and then we have all the necessary cross sections that were produced, and they are defined in the template that originated this bridge. We need all these reference lines to produce this drawing, this cross section. We have the lead in the sidewalks, okay, that at the end is scattered by Boolean operations with those laminar elements that we previously saw. We have reference points for the position of the rail for the pedestrians, and also for a small element prefabricated that is positioned here. We have different cross sections along the deck because of the extremities of the deck, because there is a slight difference in 10, 20, 15 centimeters, and that is modeled. Okay, and also because we have a transverse beam at the end of the deck to improve the solidarity of the different prefabricated beams. The difference between the other cross section, it's not complex. In this case, is a cross section that is used to position the handrail. Here we can see the reference point. It was not present on the other or for the other section of the deck. There are two different kinds of handrails with different lengths, and so you have to have the two different cross sections. In terms of the 3D model, we have girders, piers, and link girders. The piers, the expected information. There is one pier for each support. The abutments also are produced on this way, and then the other elements of the abutment are introduced by a smart part positioned at a reference point. In terms of the deck is in reality produced by link girders, but a link girder has to start at a reference point and end at a reference point. And so the reference points are introduced using girder elements that are connected to the main axis of the bridge. So that's this element. This element you use to introduce the reference point, start reference point of this span. Then the other element here produces the final reference point for this span and the start point of the second span, and so on. With this, we produce the reference points to introduce the link girders. We have a template for the precast deck in full with every element, okay? And we also have a link girder for the slab cutters, what we call the laminal elements, to introduce a Boolean operation of 1 centimeter and to create the joints between the prefabricated elements. Okay, and also this one for the sidewalks, the leads of the sidewalks. With this, at the end, when we are seeing the model, we are talking of the 3 independent link girder for each span. It's not complex to implement, especially when we start using, for example, this is a 5-span bridge. Okay, we can even more speedily change this to other kilometer to transform this in other bridge. Okay, because it's only a question of changing the kilometers of the piers and of the girders, and everything adapts. So we have the girder for each span, the deck here 1 to 5, and the cutters 1 to 5, and then 1 to 5. There are things that have to be manually adjusted because of the distribution of the girder deck in each span. With this, we produce what we see here, and then from here we extract the 2D drawings for each bridge. As I said, the process is optimized in order to minimize the specific drawings from each bridge. We have only 3 or 4 general geometry drawings for each bridge that shows the bridge in its full length, and the details for the piers, for the foundations, are from drawings that are uniform for all the bridges, and that they have a parameterizations in terms of elevation for a foundation, in terms of height for a column, and things like that. Just to finish, I would like to show this 1 kilometer railway bridge. We started doing this bridge using a template with a small number of spans, and then using the addition of the TCL file, we quickly added more spans using the previous defined spans and inserting some lines in the TCL, and at the end we produced this bridge completed and rigorously defined in a matter of 2 hours. Okay, I believe that that would be impossible with any other software and any other workflow prepared, and how to produce the drawings. You can see here that all the elements regarding the railway bridge that I have referenced previously in the other bridge and in the Operan bridge are present. We can see here the laminar elements that are used to cut. They can be disconnected because they have a specific IFC classification, and also the other elements we used, the girders we used to implement the reference points for the bridge deck, can be quickly disconnected and hidden. So this is how we produce a railway bridge with 1 kilometer in about 2 hours. I will show you now the overpasses. So this is the template for an overpass. The overpasses are 95% of the cases with 3 spans. The deck is continuous along the 3 spans, is supported by prefabricated I-shaped beams. There's a prefabricated slab that works as a formwork for the pouring of the concrete of the slab, of the final slab deck, that allows for an integral functioning of all the elements of the deck. In this case, we don't have bearings. The beams rest directly on the piers cap and on the abutments. Here you can see that the abutments are defined in the whole plan bridge, with the exception of the transition slabs. The transition slabs are smart parts that are positioned using a reference point, and we also can see here the cutter for the prefabricated slabs. In this case, this is the template. The cutter exists, and that knows, but in a normal overbridge, the cutter after the booling operation is eliminated. So let's go to Operan bridge. So we have the road X, the offset axis, as I explained it, all the cross sections. These ones are all simple cross section with no major complex. Of course, the decks is a little more complex. In this case, we have a slight variation of the concept of the modeling, because we have to have a round curvature in the surface of the road, and when we were talking about the railway bridge, it was the ballast that had a variable thickness to achieve the circular vertical curves where applicable. When you are working with prefabricated beams, or the depth of the deck slab is variable, or the thickness of the asphalt layer is variable. For sake of the construction efficient, or in terms of reinforcements, it was considered that the thickness of the deck slab was uniform, and that the vertical curve was achieved by using a variable thickness in the bituminous layer. So at the end we have a Boolean operation between the deck and the asphalt layer, and from that operation, the bituminous layer subtracted from the deck results variable thickness in the asphalt layer. We have also the girders. Okay, this case the wings of the abutments are produced here. Okay, we also have elements for the introduction and reference points for the girders, the link girders of the deck. And also you have, of course, the piers, the abutments and the central piers as usual. Then we have the girders. Okay, at the end there is a girder for the deck beams, a girder for the deck slabs. Okay, and also other elements necessary to compose the overbridge. The methodology, the workflow is similar, but there's some slightly difference because of the inexistence of the bearings, and also because the vertical radius of curvatures are much less than in a railway bridge, so the geometries difference imposed by that situation has to be considered and to be adjusted regarding that. Here you can see one of the few underpasses that we have got in all the length of the project. This was also modeled using Oplan Bridge. In this case, for a question of experience and understanding how to do things, we decided to model a stretch of the road and also of the railway for a better visualization and understanding of the solution by the different stakeholders. This is at the end, it's a frame, closed frame underpass with a constant geometry. So on the side of Oplan Bridge, what we have modeled is this. Okay, this is not complex, so we have a closed cross section and mainly the cross section for the retaining walls, the walls in the extremity without a top slab. So in the end, we got this. We also modeled the New Jersey barrier, rigid barrier here, also the rails and the blocks for the bridge. Until now we have only seen modeling of geometries, but also in the Nigeria project we have decided to start implementing the drawing modeling of the reinforcements. And so, as in Quadrante we like a big challenge, we decided to make our first reinforcements in this underpass. And so this is the complex result that came from that drawing. Following our first reinforcement challenge, we decided that was a good idea to model the reinforcement in one of the bridges. And so, element by element, we finally achieved the total modeling the reinforcement of one bridge that is used for the other bridges. This is a heavy model. We have the reinforcements of the abutments, we have reinforcement of the prefabricated bridges and the deck slab, the pier cap, the columns and the foundations. Only one element is lacking the reinforcement, it's the piles. Okay, we are working on that. I believe that by next year we will achieve the reinforcement for the piles. Hello again, thank you very much for your time. I hope you find it useful, our presentation. Of course, it's an overview of everything what we are doing, of our workflows. That would take hours to get into the details. But anyway, it was a pleasure to be here. See you next year with new challenge and new overcomes, new experience. Bye-bye.